Ladies and gentlemen, I welcome you to my guest lecture, Free RTOS, an Introduction. My name is Danіеля Fішера. I'm professor at the University of Applied Sciences in Offenburg. It's in Germany, in the southwest part, where the Black Forest is. Okay, today I want to give you a short introduction to Free RTOS. We first start with something about software architecture. It's important to know. Then the next part will be Free RTOS and very shortly how to install it. Then we start with the functionality of Free RTOS with task and scheduling, and a very short introduction and an example how queues can be used. Okay, here's some recommended books and links. Generally, for embedded software design, I can highly recommend this book from Jacob Beningo. If you work in the future or now more also with ARM Cortex controllers, then I can highly recommend this book. Here you can see a link where you can find Free RTOS and a lot of information about it. And here it's, it's a PDF where all is explained in detail. Okay, before we start with the content, we start with a small C puzzle. You can see here a C puzzle, very simple example. What is printed out on screen? Maybe you can write what you think into the chat. What do you think? What is printed out here in C? You can see here we have integer variable. Here it's incremented by this, and at the end it's printed out. Any ideas? Yes, it's really an interesting puzzle because it's very ugly code. 24 is one. No, sorry, unfortunately not. Okay, I will show you. 0 is printed out. Why? You can see here very, very ugly code because in this code, something went wrong here. Maybe the one who programmed it wanted to write E is 0, 0.0, and the one who wrote it put here a comma into it. And the comma is really, it's an operator in C. C has a comma operator. And everywhere where you can write a statement, you can write 2, 3 or more statements separated by commas. Okay, let's start what's happening here. First, this part of the for loop, we assign 0 to E, that's correct. And then the next statement is 0. And this 0 doesn't matter. The compiler will not generate any machine code for this 0. Also here on the right-hand side, you can see the part which is executed always at the end of the loop body here. And in this part, we also have this wrong comma operator. And now what happens here? E plus 2 is assigned to E. Okay, this is a legal statement. And the next statement is a 4. And here from this 4, no code is generated. Okay, but now we look inside. This is the condition whether the loop body is executed or not. And here the comma operator is also separating 2 statements. This is the first condition, E smaller 10, and the second condition is a 0. And here really nobody knows exactly sometimes what happens here. And now here, the last condition is used for this decision whether the loop is executed or not. And here it's a 0, it's false, and it's not, and therefore the loop body is not entered. And interesting here, your compiler is very clever. Your compiler is giving you here a warning. I will tell you what the warning is. The comma operator in a tested expression causes the left argument to be ignored. And that means here you can find the warning, and very often beginners, they don't care about the warnings, but now you should always care about the warnings. You should always check your warnings. Okay, then we start with the content here. First of all, we should talk about what is an embedded system. Here you can see a definition from Wikipedia. It's very interesting here. You can see an embedded system has a very specific dedicated function, and embedded systems can be realized by a microcontroller. Yes, I use also here a microcontroller. This is for our examples here. Maybe you can now, that does not display it, okay. I use here a Cortex microcontroller, but you can also use for embedded systems a microprocessor system. Okay, the embedded system is this field you can divide into two different parts. I will show you. First, we have our deeply embedded systems, and these are systems which you know. They are mostly based on a microcontroller like a Cortex M4. Mostly we have here a single core processor. That means inside your chip you have only one processor. We use here some software architectures like bare metal or the real-time operating systems. We will discuss this in detail. Programming is done in C, C++, mostly in C, sometimes in C++. These systems, they have normally no or a simple or also a complex UI user interface. The non-deeply embedded systems, systems like based on a microprocessor like Cortex A53. Here we have mostly some multi-core chips. As an example for such a system is the Raspberry Pi. You have there sometimes general purpose operating system, sometimes with, sometimes without a real-time extension. As an example, embedded Linux or something like this. Here you will find mostly as programming language C++ and sometimes C. If these systems need a GUI, mostly currently Qt is used for the UI, for programming of the user interface, and Qt is C++ framework. Okay, we will consider now in our lecture today deeply embedded systems. We will now talk about deeply embedded systems with a microcontroller and also how RTOS is applied in deeply embedded systems. Okay, what should we also know? Very important is what a deeply embedded system is doing. A deeply embedded systems, they must perform several tasks at the same time. I'll show you here some examples. You have to read sensor data. You have maybe write data to SD card. Maybe you have a display on it and you have to print something on the display. Maybe you have the need for self-monitoring and diagnostic. Maybe you can implement there a control system on it. You can receive data via CAN bus. You maybe have always to read the buttons, if buttons there, and so on. And maybe you want also to check is the battery full or not. And these things have to be done at the same time. The problem is now you have to do several things at the same time. And you have only a so-called a single core microcontroller. That means in your chip, there's only one core. But now the question is, how can you perform this? And the answer is you need a software architecture which is supporting you with quasi-parallelism. I show you the possibilities. There are four different kind of software architecture. And with this architecture, you can implement quasi-parallelism. Okay, maybe some of you know the first architecture. It's called a super loop without interrupts. I added this without interrupts. This is an architecture which is mostly used in the field of the Arduino. Often there you can find this architecture. The next architectures are more and more complex. I will explain this more in detail in the next slides. You have the super loop, there we use interrupts. Then there is architecture, it's called function queue scheduling. Then there is the last architecture. This is what we will discuss today a little bit more in detail, is an RTOS. Also here you can use interrupts. Okay, some challenges here. Normally in the super loop, there is nearly no challenge for you. It's very, very easy to implement. The other architectures, they have really a kind of problem. You have here the shared data problem. That means nearly at the same time, a different part of your program, interrupts, task, or the main program, they can access at the same time global variables, and then they can be corrupted, and this is called the shared data problem. Also, you have to handle something with interrupt time problems. That means sometimes interrupts are coming maybe too late because other interrupts are more important. Here you can see the first three architectures. They do a kind of multitasking, which we call cooperative. That means each task here, what you can consider later as a task, has to finish some functions and then giving the control back to other tasks. Here in a real-time operating system, we have also the possibility, and this is what we are using. It's preemptive. That means a higher instance. There it's the scheduler can stop running tasks and other tasks later can get the control and can get the CPU. Here we use sometimes some nicknames. The first three architectures are called bare metal. The last one is called RTOS. Okay, and really 65% of all new deeply embedded projects, they are using now RTOS. It's also very, very common now that we use an RTOS in new embedded projects, and this is the state of the art. Okay, let's have a very short look into all architectures here. The first one is the super loop, here without interrupts, very, very easy to implement. You write a main function with an endless loop, and in this endless loop you call your first function, the second function, and the third function, no problem. And each function can write and read global data, global variables. They can communicate in a very simple way by using this global data. It's very, very simple. You can see now here on the timeline, we have a function. Function 1 is executed, function 2, function 3, okay. And then it starts again, function 1, function 2, function 3. Okay, what happened here? You can see function 1 is executed a little bit shorter. Function 2 lasts a little bit longer. Yes, that depends maybe on some global variable. Sometimes a button is pressed and function 2 has to do more work, and no button pressed, function 1 has to do nearly nothing. And that happens in this super loop without interrupts. Okay, the super loop with interrupts, very easy at the beginning. You have exactly nearly the same structure like on the left-hand side, but now we are allowing interrupts. That means somewhere inside the code, an interrupt can happen and is stopping the running function 2. And now you can see first the interrupt is executed and then function 2 is ending and so on. You can also see what can happen. 2 interrupts can be executed and so on. Okay, this is the second architecture. The third architecture is a little bit difficulter to program. You have to implement in your code a queue by your own. Mostly we use here some linked list or ring buffers. You have interrupt. The interrupt is considered as the producer. That means the interrupt is detecting that something has to be done. Maybe a button is pressed or a waiting time is over. And then this interrupt puts an element of a struct. You can see this is a struct inside this queue. The struct consists only of a function pointer. This function pointer can be used later for the consumer. The consumer later can execute the function by using this function pointer. And if you want also to handle priorities, you can also add here an extra element into this struct, which represent the priority. And if you want to use this priority, then you have a priority-based queue. That means you put the elements not always on the left-hand side in it. No, you consider the priorities. That means on the right-hand side, you can see the task or the tasks later, which have a higher priority. They are put in on the inside in a sorted way. So the consumer is always reading and executing the task with the highest priority. As an example, just to show it here, you can see an interrupt is coming. An interrupt puts an element into the priority-based queue. Then the consumer is executing it, and so on. The next interrupt is coming, putting also something inside the queue, and so on. This is called priority. This is called a function queue scheduling here with a priority-based queue. A better way and with more functionality is that you use an existing real-time operating system. Here you can see the basic principle of it. It's only a basic principle. We have here inside our code, we have now tasks. It's very simple. You will see later. It's only a function with an endless loop. And you have maybe here 3 different tasks. And we have only one processor. That means only one task can run. This is the green one here. The green one is running. And now there is a higher instance which is controlling the scheduling. And the higher instance is nothing else as an interrupt with a higher priority. Maybe a timer interrupt can do this. And this interrupt is checking. Should be there a context switch? That means we stop task 2, you can see, and we rerun or we restart task 3. And in every task which is stopped, which is not running, which is gray, you have to store the program counter. That means this is the position inside the code, in the machine code, where this task was formally stopped, and then you have to restart it, or the scheduler has to restart it on the at this stored location, at this stored machine code or address of the machine code. Okay, and this process is called a context change or a context switch. That means the scheduler has to do the following thing. It has to stop this task 2. It stores the global program counter here in a structure, data, which belongs to this task. And then the scheduler has to read the stored program counter of task 3 and has to restart task with this program counter. And then we made a context change and we switched from task 2 to task 3. This is the basic principle. Of course, it's much more complexer, but for the beginning, this is enough. Okay, now we switch to FreeRTOS. FreeRTOS is currently the most used RTOS for deeply embedded systems. It's available for 35 microcontroller platforms. It was developed by Richard Berry around 2003. Now Amazon took it in 2017, but still it's available for free. The FreeRTOS is implemented in C. You can see here on the right-hand side an example. It's written in C, and inside the code and in a few files, you can find also assembly language here as an example here with inline assembler. You can see here this is maybe something with assembler inside C functions. Okay, if you want to find more information about it, if you want to download it, here it's the website. On this website, you can find a lot of interesting documentation, and also you can download it here. FreeRTOS is offering a lot of functionality. I call these blocks FreeRTOS objects. This is a very important thing. You find here very, very useful things in FreeRTOS. We have here our tasks. Then FreeRTOS is offering some system tasks, but only 2. We will see later something about the idle task. You can also use software timers if you want. Then what you have a queue, you have queues. Queues are very, very useful. They are implemented in a very clever way. Here the queues, they avoid the shared data problem. So you can be sure if you are using queues from different tasks, the data inside will not be corrupted. Here we can see 2 different versions of queues here. Stream buffers and message queues are also possible. We want now later only to talk, we will talk about queues and application tasks, nothing more. And then you have also further very helpful and important features for the advanced programming later, mutex, you have different kind of semaphores, you have notifications, that means you can send a notification to other tasks. And also if you want to synchronize different tasks, you can use event groups. However, in this lecture, we want to talk now only about tasks and a little bit about queues. Okay, now how to install it. The installation can be done in two different ways. First, the easy way. The easy way is your integrated development and environment. You can see here some modern development, integrated development environments, like here I'm using STM, for STM, we use the STM32 Cube MX environment. There you can disable or enable it. That means if you enable it, if you click here, then automatically the code is included in your project. Also, there's an automatic code generation and two empty tasks are generated, and also the scheduler is started. That means if you use such an IDE which is offering this functionality, it's very easy to start with RTOS. The hard way is very complex. You have to download the newest version of RTOS. You have to unzip files, and then you have 3 directories, and here from the kernel directories you can add files to your project. But this is a little bit tricky sometimes. There you need some specific knowledge, which file you have to use, and so on. Okay, I made here a short overview slide for you. RTOS, if you add the files by your own, you have to know what you have to add. And there are files. These files here are platform independent. And that means these files does not contain any specific code for your specific microcontroller. That means these functions or these files and the functions inside, they look always the same. It's the same code for different microcontrollers. You can see here task. There inside is the code for our task. Here maybe there are the queues in it, and so on. Okay, this code has to be added. Then we have to add heap management system. You have here 5 different possibilities. There are 5 heap implementation, and you have to select one of them. Mostly, if it's done by the IDE, they mostly use heap 4. Okay. Then the most complex part is this part. There are 2 files which represent the platform. That means here inside these 2 files, you can find specific code for your controller. Each controller has different registers and so on, and this is implemented here. And also here inside this code, it's the code here inside is using inline. assembler code, and therefore it depends also on the compiler. That means if you want to implement the FreeRTOS for your specific controller, you have to know what kind of platform you are, and inside this platform in other subdirectory you can find then for this platform and for this compiler. Okay, you can see it's really a little bit difficult here if you do it by your own. And then, very important, your FreeRTOS is configured by a header file. This is very important. Inside this header file, you have to you can do some configurations, very, very important. Okay, what can I say about the heap? Yes, if you program with FreeRTOS, you have to create tasks, you have to create queues, all we will see later. And if you create them, you need memory, and this memory is managed by the heap. By the heap implementation, only one heap implementation, heap 3, is using the real heap, what you maybe know now, and the other heap implementation, they use internally module global memory. Okay, next we should talk a little bit about this configuration. The configuration of the FreeRTOS is done in this very important file in FreeRTOS config here. This file is really large, maybe 4 or 5 pages on screen. Here you can see only some content of it, and there you can see what you can maybe do. You can enable here maybe the floating point unit, the memory protection unit, and so on. But at the beginning, it's important to know the most important thing. The first thing is here we have to configure the heartbeat of the FreeRTOS. That means with this frequency, the scheduler is later checking, should there be a context change or not? And this is the tick rate. In my example, it's 1000 here, the 1000 hertz. It means after 1 millisecond, the scheduler will check, should there be task change, a context change or not. Then the next thing is here, you can configure your heap size. This is the size from where the memory is coming from for your tasks and for all FreeRTOS objects. Okay, that's all. Step by step later, if you are using FreeRTOS, you get more and more familiar with this config file and what the meaning is of these defines. Okay, now we start with the most important thing, with the scheduler and how to create tasks. Here you can see a very simple example how we create tasks. Here tasks are created. Here 3 tasks are created. It's very, very important to know this function. This is the most important function in FreeRTOS. Here you can see the function name is xtask create. Where's this name of the function coming from? Yes, they use internally a kind of programming style guide. Each function, each API function in FreeRTOS is named like this. The name consists always of 3 parts. Let's start with the part on the right-hand side. This is how you would name a function, create. That means on the right-hand side, you can find what the function is doing. Then here, what is this? This is really the name where you can find the function. The function is inside the C file task.c. That means they took the name of the module inside this name of the function. It means every time you see a API function of FreeRTOS, you know exactly in which C file it's implemented. This is in task.c. Then on the left-hand side, you can find the return value, the data type of the return value, and they use the X for FreeRTOS specific data types. Also, there could be some native data types in it, and this is also coded inside the function. And this is very, very useful. It means if you see somewhere inside the code a function from the FreeRTOS API, you see directly what is the kind of the return value, what is the kind, where can you find this function? This is coded here, and what is this function doing? Okay, this is very simple. Later, of course, we should check that the return value is correct and so on. And now here, the scheduler is started. After you created your task, then we start the scheduler. The API function itself is really simple. Here you put here a function pointer to the task function. Here you can give them a name, the task, very useful, we will see later. Each task has its own stack. Here you give the stack size in words. This is in words. A word is here 4 bytes on our platform. Then you can pass parameters, maybe not necessary. Then we have here the priorities, and here we can put also, if we want a pointer to a task handle, and FreeRTOS is setting this pointer then to the correct handle. And here the scheduler is started, and tasks, they have all their own stack. What we should know, it's very important, the priority here is how humans are thinking. High values means high priority. Unfortunately, on Cortex microcontrollers, in interrupts, for interrupts, it's completely the opposite. So sometimes it's also for my students sometimes not clear what is the meaning of high values. But here in FreeRTOS, it's like we humans are thinking high values, high priority. Here in detail, it's very easy. This function X task create has 3 optional parameters. That means it's not necessary that you use them. If you don't use it, you can put a null instead of a concrete value. That means at the end, you have only to pass a function pointer of the task function, the stack size, and the priority. It's really simple. And then at the end, you get a return value. You can see this is a specific data type of FreeRTOS, a specific data type, and therefore this X is used, that you can see on the name, with name of the function, that a specific FreeRTOS data type is returned. And later, of course, you can check, is it working or not here? Normally, you should implement this like here. You should create a task. You get as a return value this one here. You have your variable, a local variable, and in this variable, it's stored whether the creation was okay, then you get back a PD path. Or if it doesn't work, maybe there's not enough memory available, then you get this back. I'm using very often in my programming courses the assert statement. Assert it's a macro, it's implemented and it's defined in assert.h. And then I use this. And if this is not correct here, then I get here on my system print out in a window. Okay, that's all to know how to create a task. And now we have to talk very shortly about the idle task. It's not so easy to understand at the beginning, but in FreeRTOS and of course maybe also in other RTOS systems, always a task should run. And if you have the situation that no application task is running, then there must be a task, and therefore the system is generating automatically an idle task. That means if no other task is running, then the idle task is running. We will see this later here, how the idle task is displayed here in my notation. You can see here the priority is low, the type of task is a continuous task. You will see later what it is. Okay, in the idle task itself, there's only an endless loop, nothing else. And in FreeRTOS, there are only two system tasks, the idle task and a daemon task. Both are created by FreeRTOS, so it's no need for you to create them by your own. It's always done by FreeRTOS. Okay, this is the idle task. Now we want to talk about a real application task. And there we should know the task state model. Each task can be in two different states. Here you can see the beginning of a very important state chart. Normally, yes, a task can be in not running. This is a state. And the other state is running. Running means the task is executed by the processor. The code of the task is executed. Okay, the other situation or the other task is it's not running. And here this is a super state. That means inside the state you have three substates, and these are the three substates suspended, ready, or blocked. Okay. Let's start with ready and running. A task can be ready. That means there's no limitation. The task is ready. The task is not waiting for something. Then it's ready. And then if the scheduler decides to execute the task becomes running. If the scheduler has to run another task, this currently running task is preempted, and then this task becomes ready, and so on. Okay, you can see a task can be in this endless loop, ready, running, and so on. We will see this later in an example. Okay, this is these are the most important states, but there are two other states which can be very useful. The first state is the suspended state. The suspended state is a state where you can exclude tasks from the scheduling. That can be very useful if you don't need a task for a long time. Then you can create them. You can create this task, and then you can put them into the state suspended, and you can see you can put them into the state suspended, and then this task will not be considered from the scheduler. And later, if you want that this task will be considered by the scheduler and can become running, then you can put them from suspended into ready. Here you can see the API functions, also very useful. Task, task suspend. Has anybody an idea what is V means here? The first character, maybe you can write this into the chat. What could be this V at the beginning of the API function? What is the meaning of this? Has someone an idea? This is the return value. The return value, and this V stands for void. That means this API function does not return a value. And this API function is implemented in task.c. Okay. The last state is the block state. Sometimes it can happen that an API function is blocking a task. For example, you have a running task, and the task is waiting for data in a queue, and the queue is empty, and then the task must wait until data is available. And then FreeRTOS is setting this task from the running state into the block state. That means also in the block state, the task is not considered anymore for scheduling, and only if there's an event could be that data is available or something like this, then this task is entering the ready state. And here, what I mentioned before, it can happen that no of your own created tasks are running, and then the idle task is running. We will see this later. Okay, task model, very useful to know, to understand what's going on. Each of these real-time operating systems, they are offering different kind of scheduling algorithm. A scheduling algorithm is an algorithm which is used by the scheduler. This is the part of the code which decides which task is running, which task is ready, and so on. And here we have at the beginning, two different scheduling algorithms. There is a possibility to run your program with a scheduler which is called round robin. This is the first one. This is possible to use for simply application. All tasks have the same priority. An idle task here is not necessary. The task don't relinquish control. That means you don't have to give the control back. This is done all by the scheduler. We will see it. For real-time application, it's better to use fixed priority. Tasks can have different priorities. An idle task is not necessary. Task, they can relinquish control. That means a task can give back the control to other tasks. We will see this in an example. And also they can be preempted by the scheduler. And FreeRTOS is offering the possibility that you mix both of them. That means you are in a mixed mode. And this is a very useful kind of using FreeRTOS. A task with a higher priority they run with fixed priority. Here you can also enter the part of your code which is real-time dependent here, and other tasks which are not belong to any real-time constraints, they can run in the background with the lowest priority. Okay, here we'll see this as an example. Here we created here 3 tasks, very, very simple. The scheduler is started. And here you can see an example of the implementation of such a task function. You can see this task function is here, this task function, and if you put the name of the function here in, it's considered as a function pointer, and then the scheduler can execute this task. Inside the task, you will see there is the typical endless loop, which we find normally in each embedded program. But here in every task function, you can find now this endless while loop. Okay, there are some switches or configurations in FreeRTOS config, which are useful for this example. Here you can see the heartbeat. Very important, priorities must be equal. This is very important that they are equal. This kind of task has a name, a specific name. It's a continuous task. Continuous task, here they are running always through this endless loop. And it can happen now that task is running maybe a really large number of loop counts where this task is executed, and somewhere inside it's preempted. This is very important to know, and later if the task becomes running again, it's restarted at that point. Here I have only a comment here, work to do. Here you put normally your own code in it. This is what the task has to do, and I only put here a comment for this. I think the easiest way is now to understand how it's working. I'll show you the IDE. Now you should see hopefully the IDE, which I'm using here. I'm using the STM32Cube IDE, and here we can enter the main function. You can see here, this is the main function, the entry point of the code. Here we enter a specific function of mine here, and in this function we always configure our system. And here the endless loop of the main program will never be reached. Okay, now we jump inside this application file, and here you can see the part where we create 2 tasks, where we start the scheduler. Here we never reach the point here. After calling this function, you will never come back to this statement here. The code is running then only in the task functions. Here at the beginning, I print something on screen, nothing very complex. It's only output on screen. Then we have here our 2 task functions. They only increment something here, a variable, and print it on screen, nothing else. Here what I'm using always is this assert functionality. That means if there is something going wrong, like here, if it doesn't work to create a task, it jumps inside this function, and there it sends it via UART a message. So you can start a terminal program, and then inside this terminal program you get the error message. Okay, this is the thing, and I will now start it. I will now start it here again. The program is now started here. First it's built, okay. Now it's at the beginning of main. I started, okay, now the program is running. And here, hopefully you can see it. It's a very, very useful tool. It's the tool System View from the company. It's a company here in Germany. The name of the company is Zegger. And with this tool, you can see how the scheduler and your program is working. I will stop it. Here, I enlarge it a little bit. Here, you can see how it's working here. On the timeline, your task is running. Then red, a timer. This is the SysTick timer. It started here every 1 millisecond. And the timer here, this SysTick, triggers a specific part of the FreeRTOS, the scheduler, and this scheduler is doing the context switch to task 2. You also can see how long this context switch lasts. 5.4 microseconds and 7.5 microseconds. Okay, and here you can see maybe on the timeline here above, every millisecond the SysTick is executed. The SysTick triggers the scheduler, and the scheduler is switching from one task to the other. We have 2 tasks, and you can see this is the round robin, task 1, task 2, task 1, task 2, and so on. This is the simplest scheduling algorithm here in FreeRTOS, the round robin. Okay, I close it here. I close this one. And here we have again a screenshot. Here you can see the heartbeat here of your system, which you configure in FreeRTOS. And based on this heartbeat, the scheduler is now switching from one task to the other. Here you can see an example with 3 tasks. In our live example, we had only 2 tasks. Okay, this is round robin. The second scheduling algorithm is the so-called fixed priority. In fixed priority, we can use different priorities for our task. You can see here in fixed priority, it looks like the first example, but the only difference is that we have here, we can, if you want, we can use different priorities, higher value, higher priority. The implementation looks a little bit different also of our task functions. We have now here different priorities, and we have now so-called periodic tasks. The periodic task here, what is the difference compared to continuous task? The difference is that you have here a function call of the RP function, vTask delay, or vTask delay until. And here you can put your task into a block state. That means the task has to wait until this time is over. 2 possibilities for our lecture. In our example, we will only later use this one, the vTask delay. but both are possibilities to implement a periodic task. Very important now compared with the continuous task is that the body of this loop is executed only once. That means here work is done once and then the task becomes blocked for a specific time in milliseconds. And then later, if the task become ready again and then running, this work is executed once. Okay, here we call this the control is relinquished. That means here we give the control back to our system, to the scheduler. We put our task into the block state. That means the scheduler can put other tasks now in the state running. Okay, I show you this as an example here. I reopen my my IDE. I stop it here. Then here I have to use another C file. First, I have to exclude the old one, and then I have to use this one here. Okay. Here you can see we create here 3 tasks, different. We have here different priorities. Here, very simple. The 3 task functions. You can see each function is waiting 5 or 6 or 7 milliseconds. And here I'm using some simulated work to do. Here I simulate the execution of the task. Of course, you should not put this later inside your code, but here normally you put your own code in it, what the task has to be done. But I use here my own macro. It's a macro here, very useful macro. This waits of this microseconds. Also just that you know what's this. This is inline assembly into a while loop. While 0, this is a pattern which is used in C here for macros, which consists of more than one line. Then always this do while 0 pattern is applied. Maybe you will see this later in some code. Okay, that means what we are doing here, we wait here, we execute this macro here for 2 milliseconds. The macro is receiving microseconds. That means here it's doing some work for 2 milliseconds, then it's waiting 5 milliseconds, and so on. And task 1, task 2, task 3. Okay, we started again. I will compile it. Very important here, 0 warnings, very important. 0 warnings. Okay, still compiling. Okay. Now it recompiles the whole project. Very important, 0 warnings. Okay, then I start the debugging here. Okay, starting here, I run it. Okay, now my program is running. We switch back to our stacker tool. I start the recording here. Now the recording is started. Oh, you can see something is going on here. I stop it. Okay. Now look inside. We can see here Here, task 3 is running here. And now you can see task 3 is now preempted by task 1. Task 1 has the highest priority. You can see here. And after task 1 is finished, task 3 is running again, and then task 2 is coming. Also here you can see here, task 2 is preempted by task 1 and is finished here. And here in the tool, you can find everywhere this preemption on different times. Preemption happens. But what you can see here, task 1 has the highest priority, and task 1 is always executed and is always running at the time which you want, because no other task has a higher priority. You can see here the time distance between task 1 and the next task 1 is always the same. Very interesting here, what we can see here. You can see here at that time here, no task is running, and then the idle task is running. You can see here, this is the idle task. Also here above, you can see here that here the idle task is running, and here the other tasks. Of course, if we zoom into it, like here, you can see the SysTick can change the context also here. What happens here? Here, if task 1 is at the end, and if task 1 is relinquished the control, then task 1 is triggering the context change directly. This is done here. You can see the scheduler, and the scheduler switches here back to task 2. Very, very useful tools, this one. Otherwise, it's really hard to debug if you don't have this tool. And with this tool, you can see which task is running. And here that we see here something like this here, that we see here a kind of workload. I have to always to use this macro here. This macro here is responsible that you see some execution of the task, but it's only a simulated execution of the task. Normally, you should, of course, put here inside your own code, the code which is the task's main task to do, executing a specific kind of code, reading buttons, doing some control, or sending data with a bus system or something like this. Okay, this is the so-called fixed priority. It's very important, this kind of scheduling here. You can see the slides. You will also later get the slides as PDF. Okay, here we can see it. This, what happens here is task 3 is preempted by task 2. This is called preemption, and you can see at the end later here task 3 can finish. Then also this can happen, depends on the times which you entered for the delay, or how long a task is in this execution part. Also here, task 2 is preempted by task 1, and after task 1 finished, task 2 can finish, task 3 can finish. This is the fixed priority. This is the fixed priority. And here, always, if there is nothing to do, if no of your own tasks are running, automatically FreeRTOS is executing the idle task. Now we come to the mixture of both. We learned now something about the round-robin scheduling about the fixed priority. And now we have the possibility to mix them. Both scheduling algorithms can be mixed, like what you can see here. And now we want to discuss what kind of priority should they have. The periodic task, we want now to have 2 periodic tasks, and now we want to have some continuous tasks. What could be the priorities? What do you think? Task 1, task 2 should be periodic task 3 and task 4 should be a continuous task. Has anybody an idea what should be the priorities for this example here? Higher number, higher priority. What could be here the resulting priorities? Has anybody an idea about it? First of all, the priorities of the continuous task, they must have the lowest priority. This is very important. If you mix it, the priorities of the continuous task must have the lowest priority. The lowest priority. Okay, and they must have the same priority. And the periodic tasks which run in fixed priority, they must have a higher priority. Here an example, what we can do, we can configure it in such a way that we give the periodic task the higher priority and the continuous tasks, they must have the lowest priority. We will see what happens if we don't do it. Then we can see what happens. Okay. In mixed mode, we have the possibility to give tasks which should be real time, should run in real time. They can run as a higher priority periodic task, and all which should be done in the background, which does not have any real-time constraint, they can run in the background, and and therefore it's very useful if we put them as continuous tasks in our system here, that we need them in such a way. Okay, I will show you again this example, very important now. If we have a continuous task here, the idle task is not required. The idle task is not required. This is very important. The idle task is now not required. We will see it in our code. Now back to the code here. Go back to the code. We have to exclude the old file, and then I have to include the new one here. Okay. New one is included. The mixed mode. We compile it. Very important. No warnings. Normally, you should always configure your compiler with create warnings as errors. That should be done always. That means if there is a warning inside during compilation, the IDE does not generate code. You can see no warning. All is done correctly here. Here we have them mixed mode. Let's check. Okay, here in mixed mode, I have 3 tasks here. This example, and you can see, okay, mixed mode, we have to delete that one here, mixed mode, delete it here. That means task 3 is now running as a continuous task, here in mixed mode. Okay, that's the lowest priority. Okay, and now I will compile it again. And now we execute it here. Now it's running. Now we check it with our, we check it here with system view. Okay, it seems to be running. Oh, sorry. Let's stop it. Okay, sorry, I added the wrong file. Here. Oh. Yeah, in this example, I had two tasks. I added the wrong file. Here we have two continuous tasks. This is task 3, task 4. Task 1 and task 2 are the periodic task with higher priority. And you can see here how the scheduling is. And every time where these two, where task 1 and task 2 are not running, instead of executing the idle task, you can see here no idle task, the underlying or low priority task 3 and task 4, they are executed here in round robin. This is the useful mixed mode, no idle task. The continuous tasks are running. If the periodic tasks are not running, then the low priority continuous tasks are executed, and here by the scheduler switch from one to the other. Okay, this is the example for the mixed mode. The mixed mode, very useful here if you want to do some work in behind. So you have some non-real-time tasks and some real-time tasks. Then you put the real-time task as periodic task with higher priority, and the lower priority task as continuous task, which are running if the other high priority tasks are not running. Okay, here example again how it looks inside this Sega system view. Of course, we have a preemption also here, and inside the periodic task and then the continuous task, which are running here. And no idle task. Okay. As a summary of this task and scheduling chapter, creating task is very simple. Implementing task, yes, it's always normally very simple. But what's complex is, the complexity is that you don't have one file or one function where you configure the whole scheduling. This is at the beginning, very, very confusing, because the task creation itself is done somewhere before the scheduler is started. And here you enter the priority, and the priority has a very important play a very important role for the scheduler, the priority. Then inside your task implementation, which is maybe somewhere else in the code, in your code, maybe in another file, there in the implementation, you have to decide, is this a periodic or a continuous task? If it's periodic, you use these two RP functions. If you don't use them, the task is a continuous task. Completely different thing. And then in your free RTOS config, you can put some defines on off, like preemption on off. Then there are other things which we don't consider here, like time slicing and so on. And also there you enter the heartbeat. You can change the heartbeat of your system, also in free RTOS config. And then this fourth part is we can have blocking functions inside our code. We will see an example now. We can have blocking functions inside a queue function. And also you can use task suspend. You can suspend a task, and also this has an influence to the scheduler. It means it's not so easy to understand the whole system, because you have to check different files to understand why the scheduling is working in which way. Okay. Last chapter, a very short chapter, but a very important thing, are queues. Queues are used for sending data from one task to the other. You should now not use normally no global variables anymore also in free RTOS. For sending data, please use queues. Queues are very useful functionalities, and they are implemented in a proper way. It's tested, used by a lot of engineers in the world. That means normally there should not be a bug inside. And queues are generic FIFOs. FIFOs are data structures. FIFO means first in, first out. Generic means it does not depends on a data type. You can use for any data types, for any structs, and so on. And they are offering a lot of functionalities. Details you can find on the website of FreeRTOS. There is a huge functionality available. For example, you can also write at the front then of the queue, then the FIFO becomes the LIFO, and they are used for communication. Okay. We will see also how we can influence the scheduling. You can put a task into the block state if this task is waiting for an entry of a queue. We will see this on the next slide. Very, very important to know. Queues are managed by FreeRTOS, and they avoid the shared data problem. It's not possible that task 2 is reading and in between task 1 is writing new data in it and corrupts the data. This is not possible. Queues can be accessed from anywhere in the code, therefore, a short exception, therefore, queue handle should be a global variable. This is an exception from the formally rule not to use global variables. If two different tasks wants to use a queue, it needs a queue handle, both need a queue handle, and therefore the queue handle must be global or module global. Important also elements which you put inside a queue are a copy of it. That means it's copied inside the data of the queue, but it's a little bit difficult sometimes. You have to be very careful if you put pointers inside a queue, because later if task 2 is reading and is reading that pointer, it should be implemented in such a way that still the data is there where the pointer is pointing to. So there you should be a little bit more careful. Okay, and stream buffers and message buffers, maybe you remember from the overview, FreeRTOS objects, they are only a specialized version of these queues. Okay, now we start with a short example, how to create a queue. Okay, here you can see this global queue handle. If it's global, everyone has inside the task function, any task can have now access to this queue. Very important. Here, also some implementation details. If you use a queue, you have to include this header file and always include the header file after you included FreeRTOS.h. Here the creation of the queue, very simple. Also here you can see create. The function is inside queue.c and it returns a FreeRTOS specific data variable with a specific data type. This is a specific data type of FreeRTOS. And then we have to check whether this function was successful or not. If not successful, the handle is null. Yes. Queues are generic. That means on the creation you have to tell this function how many elements you want and what's the size of each element. And then internally it allocates, by using this specific heap of FreeRTOS, enough memory to store 10 multiplied with this size of variables. Maybe you are wondering what this is. In embedded programming, you should not use the native data types like int or something like this, or short int, or unsigned short int. No, in embedded programming, we are using these type defs, and these type defs are inside the standard int.h file, header file. And here you can see this is an int variable, a signed int variable with 32 bits. Because int itself, the size of an int, depends on the specific platform. And by using these type defs, you see directly how many bits or bytes inside this used data type. So never use int, char, or anything like that in your embedded code. Use these type-def data types. Okay. Here, number of elements, size of one element. This is what I explained. If null is returned, no memory could be allocated. Internally is this also, this is a type def also. You can see _t, and internally it's nothing else as a pointer to a structure. Okay, queue creation, very, very simple here. And now let's see what we can do here, how to write to a queue. Here you can see, here we write to a queue, very, very simple with this function. And here a special case is if the queue is full, what to do. And then it depends on this parameter. If the queue is full, then what to do. If it is 0, then the program is executed in a regular way, and if it's greater than 0, then the task becomes blocked and is not running anymore. Okay, and here we have to check, was it successful or not? Okay, here we have to put a copy inside. That means we have also to put a pointer to the data which we want to store. Reading from a queue is very similar. Here some examples. Also here, the special case, queue is empty, then what to do? Exactly this. And here we have to pass a pointer to our variable. And if all was correct, then later in our variable, which we pass the pointer, the stored value is in it. Okay, as a summary of the whole course, what have we learned today? RTOS is the most promising architecture, therefore use it later in the future. FreeRTOS is the most widely used FreeRTOS. The manual installation is very difficult. As I told you, if possible, use the functionality of the integrated development environment. If they offer this functionality, use it. We learned something about scheduling algorithm, the fixed priority and the round robin. Also a mixed mode is possible. And there are 2 different tasks available, periodic and continuous. We learned something about priorities. And queues are used to exchange data between tasks.